Okay, good morning, everybody. So I'll be taking this session. Our first speaker today is Alessandro Ederoclite. He's a tenure track astronomer at SKA, and he's going to be talking about stellar accretion in OAG surveys, an optical window for the SKA.
All right, so thanks very much. I have the beautiful privilege of being the first speaker after the dinner. And yes, I'm a tenure track on time domain astrophysics here at SKA, and I am the outlier of this conference. I'm possibly the only one who is within this galaxy. And I'm an optical astronomer, so I have no idea about your jargon. So I spent some time this week. So for the users of you, for those of you who use, see if I manage to do it. For those of you who like Python, remember you can use AstroPy to convert between units. This is the one equation that I decided to include for Carlos' sake. Just remember that we actually speak similar things. When I speak magnitudes and you speak Jansky's, they are actually related. And believe it or not,
hey, Alec, I think it was many years ago, right? I did my journey from the gigahertz to the. So that's your time.
This table for me was very, very useful because I started to figure out, when I used to speak about gigahertz, and go like, oh, really? So gigahertz is something meters. So most of what I'm going to say would not have been possible without acknowledging this gigantic figure of astronomy, Brian Warner. Most of the connection in accretion astrophysics between UK, South Africa, and Spain you can trace it back to this guy who sadly passed away early this year. I assume next year in the General Assembly at the IAU, there's going to be something to remember him. So, on to topic, accretion is an ubiquitous phenomenon in astrophysics. Scandinavian collaborators, 2015, they hopefully convinced us that basically you apply the same physics no matter if you're accreting on a young stellar object or a supermassive black hole. The beauty of this is you can trace back the physics of accretion basically to one paper. Sakura Sunyaev, 1973. This is, for those who care about these things, is the 5th most cited refereed paper in the history of astrophysics. This has more citations than first exoplanet, whatever. And is either the first or the second paper which has not been awarded a Nobel Prize yet. And I want to give you an idea between radio and optical of different accretors. So, can anybody guess what we're looking at?
Radio jets.
Radio jets. What do you have in the center? How? So this was a Nature cover by, and if you ever met Felix Mirabel, he's very proud about this. He basically mentions it every day. And this was a microquasar. So what we have here is a stellar mass black hole. And when Juan is going to speak about radio jets in galaxies, you're not going to see something particularly different from this. In this case, what you have is a stellar mass black hole, speaking about few solar masses, a giant star which is losing mass, and the mass is accreted towards the black hole, and then there's a radio jet. One of the prototypical objects is SS433, and this is a VLA movie. And you can see why radio has had historical meaning for this kind of science. You actually see the jet being pushed out from the black hole. And this is, and on the on the right, you see the spectral energy distribution that you get from Bezier. And when I was looking at this spectral energy distribution myself, again, because in my universe, energy, in my universe, red is on the right and blue is on the left. I was like, what am I looking at? And then I realized that in the x-axis I have frequency. So actually, the left side, the thing that goes up, that is actually radio emission. So actually, this thing is stupidly bright and radiant. Now, the funny thing is that these guys are mostly concentrated in the plane of the Milky Way. The beauty is they're prototypical multi-wavelength objects because of the high energy due to the accretion on top of a black hole, what the sentence means. They emit X-rays, right? So they have been but this is the realm of X-ray boundaries. So they're observing X-rays, they're observing near infrared, they're observing optical, and they have radio emission. So they are prototypical multi-wavelength objects. And they have major discrepancy between theory and observations. Theory predicts that there must be thousands of them in the Milky Way. We only know a few, slightly over 100. So let me get a little bit closer to what I do. If I go to lower masses of the accretor, I get a white dwarf. And I have a nice former real star. Now it's a nice carbon oxygen or oxygen. Well, it's basically an inert stellar core with some atmosphere, and it's accreting from a main sequence star. Some cases from a giant star, let's not get confusing. The first attempt to detect what in the day for me was radio was by Ederoclite and collaborators in 2005. So they looked at high mass accretions with the CEST. This was millimeter, you may argue if that's radio or not. And they only found, well, actually they found a handful. Sorry, this slide is not completely correct. It was only when Copenhagen's published this paper in 2016 when the business completely changed for us. All of a sudden, she claims in the title, dwarf node characteristic particles with low mass accretion are significant radio emitters. And now, yes, we're talking about radio. And my Shara detected a few years ago optical jets. So all of a sudden, we start to go like, maybe there is something which is very, very similar between what we see, optical radio in the black hole regime, and we can start to think about what's going on in the white dwarf regime. So if I look at these kind of things, these kind of objects with Zwicky transient facility factory, don't remember. What they do is they take images of most of the sky every day, and this is a few years worth of data, and these are two light curves of two different objects, and you basically see lots of things. And in the case, in the lower panel, you see there's a few outbursts, but if you making a mess, I'll get it right. Yes, but if you look at the same objects through the eyes of J+, you're already very familiar with J+, you've seen the telescope and everything. You can see that in the upper panel, well, at least for us who have a trained eye, that is obviously a high mass accretion rate, deterministic variable, and the in the x-axis here now you have, does it work? Yes. In the x-axis you have wavelength, in the y-axis you have magnitude, and so this is obviously a high mass accretion rate object, and this is a low mass accretion rate object. Can I do better than this? Yes, I can. I can observe it over and over, and I can actually see how it actually changes. Instead of observing it over and over, like stupid amount of times, like CDF does, I can decide only to observe it 11 times. This brings me to speak about JVAR. JVAR is a survey led by Hector Vázquez Ramió, smile and wave, and myself with the T80. You've seen the telescope. We don't use all the filters of J+, we only use the 7 most efficient filters, plus the filter which contains the cards you mentioned, K. Our observing strategy is a little bit bizarre. I will not get into the details, but suffice to say, we basically try to observe 11 times, and in fact 33 times, in order to have and we don't have a regular cadence. Hence, we are capable of detecting variables of virtually any period within a few months. And we only observe the footprint of J+, so we calibrate against J+. So we can observe within through clouds. In other words, if J+ cannot be observed, and we can. And these are characteristic variables as seen from the observatory of Cavallambre, and you can see that CVs are actually distributed all over the sky. And this is actually what I do for a living. Sometimes on the surface of a white dwarf, you accumulate enough material that you can actually ignite thermonuclear explosions. It's only the accreted material that explodes, not the whole thing. And this is what we call a classical nova. A classical nova, since you only explode the accreted material, you can actually restart accretion and eventually have a new explosion afterwards. So in principle, all novae are recurrent. And we're speaking about a few 10,000s of years. We don't live that long, although some people they do. But some novae, they are kind enough to come towards us. They actually have recurrent times of the order of tens of years. And these are very, very interesting because we can study them in more detail. So, and this is an example. This is RS off, which is which explodes every 10, 15 years. I don't remember really. And it was the first one, and it's the bottom panel here, where not only we had a detection, but we actually saw the shape of the ejecta forming and shaping during the explosion. You have an explosion on top of the white dwarf, you expect this is symmetric. This is not. So this was observed, and we have plenty of evidence that this happens. So if you ever spoke to me, you know my obsession. T-Pixidis is another recurrent nova. It doesn't have a precise recurrence time. And it exploded last time in 2011. The top one here is the optical light curve. And since we have a photosphere which is receding, it goes towards the white dwarf, you expect that higher energy is detected after. So this, second panel is X-rays from Swift. So you go like, okay, so logically, I would expect radio to be before. Right. So in the last NOVA conference in 2012, we had Laura Chomyuk and other people and myself, we had plenty of discussion of why we couldn't observe, we didn't detect T-peaks at maximum light. It became a very interesting conversation. And then Laura ended up developing her own new double explosion model. Beauty of nova. Just to use this slide again a bit, the difference between maximum and quiescence is of the order of 12 magnitudes. So, and some of them are nearly naked eye objects. So this means that they are very, very faint. Very, very faint to me is 21, 22, 23, but they can be very, very bright at maximum. The thing is, both J plus, J bar, and LSST, they saturate roughly at magnitude 12 and 16 respectively. Hence, the maximum light here and the maximum, the part of top of the vector is completely inaccessible for these kind of targets, from this kind of projects. So possibly I'm the only one who's going around saying, you know, LSST is too big and it's not particularly useful. If you look at the distribution of novae in the sky, they're mostly on the plane of the galactic of the Milky Way. And the SKA is going to provide a beautiful set of light curves in radio. And so there, yes, we can actually test all the models that Laura was doing. The South African people, they came up with Merlicht, which is this 80 centimeter telescope which which piggybacks on the pointings of Mercat. I think this was a beautiful idea. But the relevance of telescopes like ours is, yes, we cannot possibly access the bright part, but we can access the faint part. So what we can actually do is we can think about a JPass-like survey, but in the Milky Way. There we can actually study the accretors, and with that we are actually unique. There's another type of accretor that I haven't mentioned. Those are the AMCVN stars, where you have helium-rich material which is accreted on the white dwarf. Those accretion disks with helium lines are completely unique. And again, JPass is the only survey capable of detecting them. End of the story. And they are calibrators for the LISA space mission. So here we have no competitors. So in the spirit of Synergies, by the way, a little bit of advertisement. Today is the deadline for the ESO workshop. What was that? On optical transients from LSST that we want to follow up with the with ESO telescopes. And since a lot of people here are interested in Southern Hemisphere targets, I'm one of the organizers. Come meet us. So to summarize, yesterday was the Beyond Stars. Today is Beyond Exonaut. For me, it's Beyond Exonaut Astrophysics. I love the sentence, quality, not quantity. Stellar accretion has been crucial to astrophysics, mostly for two things: time domain and multi-frequency. This is where we shine. And a JPass-like survey in the plane of the Milky Way is the required thing for the future, is what we are all waiting for. So yeah, to conclude that no compact objects were harmed, yet some extragalactic astrophysicists may feel offended. Thanks very much.
Any questions? Come on.
Let's talk after.
To colors the intro.
Maybe I'm the online audience.
And the second speaker.
I'll ask a
Okay.
question, a provocative one maybe. So you say a JPass plus survey like in the plane of the Milky Way, but we talked a lot about like how growing JPass is complicated, or you want to do it certain ways to optimize that. How easy or hard is it to like have a good JPass footprint that covers the Milky Way in terms of these constraints for how you grow in things?
It depends on how much south in the Milky Way you want to go, and it depends how deep into the Milky Way you want to go. It's not particularly hard. I mean, it's going to sound rude. Equatorial is more difficult than Milky Way because you can stay north enough that the fields are actually high up in the sky now. So you see, so it's not particularly difficult. It's not trivial, but it's not particularly.
Okay, let's move on to the thanks again.
Yeah.
Our next speaker is Alejandro Lumbreras, and he's going to talk about exploring the physical properties of emission line galaxies with J-Pass, J-Plus, and the SKA.
Hi.
5 minutes for the name of the
Hello, good morning. Thank you for being here. I'm Alejandro Lumbreras-Calle. I work here at SKA with several people, but I have also been to Granada to collaborate with some others. I am also not a radio astronomer, the first disclaimer that you have to say here. And I will talk to you about extreme emission line galaxies, how to observe them with J-Pass, J-Plus, and SKA and its precursors, and hopefully why are they interesting for a more wider point of view. And let's see if this works. So it doesn't pass the... Here, yeah. This is a bit of an outline of my talk. First J-Plus, then a small bit of science, but many other people have discussed this better than me the days before, and then a bit of a quick rundown of what is available. You'll see. So, these galaxies with very extreme emission lines have been detected for a long time already, but in the past 15 years, it's when, okay, yes, this works. It's when a few samples of galaxies that you may have heard of, like Greenpeace or things like that, have actually been detected. These are shocking because even if they are many at low redshift, they are very rare at low redshift, but you can find them at low redshift, but they share some properties with very high redshift objects as their morphology that you can see here, their strong emission lines and low metallicity. And since the JWST spectra have been available, we have been able to actually confirm this. And yes, they are truly analogs of this very high redshift object in many properties. So studying them, it's a way at low redshift to understand more about the very early universe. Oh no, it's the other way around. Okay. Why extreme emission line galaxies in J+? Why is it a good idea? Well, because we need a complete census of them. We need many, and we need them very clearly selected. And to get that J+ and soon J+ are great because they are very wide, and these objects are very rare at the low redshift. And also because you need a relatively deep survey, deeper than SDSS spectra, and also better spectral resolution than what broadband surveys can give you. So our idea is to select these objects by their the excess of emission that they cause in the narrowband filters, since they have very strong emission lines. This is the J+ filter system, and you can see here the redshift slices that we can access with narrowband filters, depending on the emission line that we select. But also recently we added a weird one, which is with the broadband filter, but I promise you this works because we have the narrowband filters nearby to select the continuum. This is a slide on my sample selection. If you naively select everything that emits a lot, like this, oh, sorry. Like you can see here, this clearly is an excess of flux. If you naively select those, most of what you're going to select are quasars, high redshift quasars, but with a simple color cut with WISE photometry, you can keep these squares, and it works very nicely to remove all contaminants, and you get a more than 90% purity and completeness. With that, you can, with those selected galaxies, you can perform SED fitting to extract as many physical properties as you can. from these objects and J plus data, and you can calculate star formation rates, stellar masses, extinctions, and equivalent widths of the emission lines. Here are some of the values. These are especially at low redshift dwarf galaxies, actually, but they can have extremely high specific star formation rate, which is the star formation rate divided by the mass. And here is a bit of a rundown of the numbers. It's except for this one and this one as well. The others are a bit more rough. They're not published. They are preliminary. Actually, you can take everything I say in this talk from now on as preliminary. But I'm going to use that disclaimer a lot. And you can see that if you start adding different galaxies at different redshifts, different equivalent width cuts, but always high, I gather for this talk actually a sample of 2,200 extreme emission galaxies in J plus at the Earth. This is how they look like. Most are like this, compact. So we've performed as well follow-up observations on the galaxies that were selected. Many, I think around 50, have been observed with the Isaac Newton telescope in La Palma. All have been confirmed at what they look like, extreme emission and galaxies at low redshift. And combining this with ancillary data, you can do things like this. You can do a mass metallicity plot where if you put other samples, the green peas, the blueberries, and also JWST objects from very high redshift, you can see that our galaxies, which has this orange, red, and yellow points, actually live in the certain of a gap between previous samples and close to other JWST objects. And soon we will have Chandra X-ray and even HST observations from some of these galaxies. So we have this. We have these 2,200 galaxies at low redshift, relatively bright, and we can provide with this data. What can we have with JPass, with more galaxies, even with more precision, especially at the fainter magnitudes? There's already a paper by Jorge Iglesias Páramo in the mini JPass area, which maybe can hint at having, I don't know, 10 per square degree at the redshift below 0.35, but this is just a quick estimate. It's a lot of variance. So now on to the other part of the talk. This is where I apologize again. What can we learn with SKA and its precursors about these kind of galaxies? Well, nothing very surprising that hasn't been mentioned, at least a bit in the days before, especially how these star formation events begin and how are they maintained. You're going to guess, well, that this has to do with hydrogen, neutral hydrogen emissions. Also, this maybe was mentioned yesterday by Ricardo, but not much more. How do Lyman continuum photons leak from these objects? And this has definitely been mentioned. What is the recent star formation history on these objects? Because we know there has been, but we have access to one time scale, but we may need something else. So this is just some quick slides describing these problems, these scientific questions that can be added. You need to have a lot of star formation. You need a lot of gas, probably. Gas at the end is the fuel of the star formation. But there are many other issues that are not clearly resolved, especially for these extreme galaxies. Do you have enhanced star formation efficiency? How is the fueling of the gas happening? Because for some of these objects, they would consume all their gas in a matter of mega years, like maybe a few tenths, but that's not sustainable. We will create another galaxy after, I don't know, 10 mega years or something. That's probably not happening, no? And also what triggers the beginning of this extreme burst of star formation? Maybe actually the inflow of gas. So of course, for this one key tracer is the H1 emission. You can see here some examples of studies that have already studied H1 in these or similar kinds of galaxies. There are some studies with extremely metal poor galaxies. This one from figure here, you can see that they sit well above the 1-to-1 relation in the mass of gas as a function of stellar mass. You cannot see it here, but this is a plot already shown before, where these galaxies which are above the main sequence and hence star formation have also larger H1 fractions. And this is a very well-known galaxy from actually the first slide is Wiki 18 was the lowest metallicity galaxy ever. And you can see here that it has a lot of gas in extended configuration around, but also with some rotation and some complex kinematics that have also been observed in orbit. And yeah, the connection between H1 density and star formation rate is not clearly 1-to-1 either. So what do we have already? Well, the studies that I was mentioning, but essentially are limited, of course, to the very local universe, even if they target the low mass galaxies, and only a few of galaxies you are actually present in the very local universe with these very extreme equivalent widths. Not, I think, not because of any specific thing, but the local you get, the lower volume you get, so the harder it is to get crazy things. Yeah. So what can SKA do that hasn't been done before? Well, better explained yesterday by Betsey, but yeah, getting to lower H1 masses, going slightly away at least from the very local universe. And we can get these large samples with some value-added data to process. The other topic that can be discussed is escape of Lyman radiation, and I think I'm going very late. So I'm gonna go fast. This is how the ionizing continuum escapes from the galaxies, which should be absorbed by the ISM, but it may go through gaps in the ISM, or it may escape from density-bounded nebula. It's not so clear, but this is extremely important for the reionization of the universe. This is the flux that actually reionizes the universe, and we are looking at analog galaxies of those that did it. So it's a really, really interesting thing to study the escape of Lyman radiation in these kind of galaxies. This can be done with, of course, with H1, but also the radio continuum can give us some clues about this. This is an example of two galaxies that have been studied at very, very low redshift. And you can see that in one case, the Lyman continuum escapes from where there is no gas, that you can see in the image in white. And in other case, there's a lot of escape of, there's a lot of radio H1 emission where there is actually escape. So it's not a very simple thing. Also, the star formation rate that was mentioned yesterday also for the free emission, yeah, it's a longer time scale star formation rate tracer, so it can tell you how bursty has been the star formation when you compare with the H alpha. And what is already available now? Well, we have this, I hope I got the nomenclature right, because I did it by memory, the pathfinders, yes, are things that are actually in the northern hemisphere, and the precursor happened from the sites where they are going to happen. So this is what is available on top of J+ DR3, which is what I'm interested in. So, well, the mighty, it's no overlap with the J+ area, so I'm not going to take it. So let's go over all of this in 2 minutes and 10 seconds. The alfalfa survey is great. You have a lot of data. It's a very large overlap with J+, and there are almost 5,000 cross matches with the J+ catalog. But with my galaxy, it's only 17. But it's interesting, and actually you can start to do science with this. I shouldn't, but I was yesterday creating these plots and checking the properties of the galaxies that do the cross-match, because they are low-mass galaxies, even for the low redshift range that this survey covers. But they have lower H1 than the typical alfalfa, but I think the ratio is higher, and definitely you can see here there's a much higher H1 mass than stellar mass, but also you can see that there's a very nice correlation. I think this has been identified before, but it was fun to me to see between the ratio of H1 and stellar mass as a function of the specific star formation rate. So the more extreme the starburst is happening, the more the excess of gas has. Probably wrong, probably missed something, but anyway, I wanted to show you. This is an image of the cross match between the surveys, and we have to go. This is a LOFAR, the low frequency survey, and there's a very nice overlap with J plus DR3, and this time I have a lot, 138. They typically, they're brighter, like 1 magnitude brighter than the rest of my sample. And there's a lack at the low redshift, I guess, because they might prefer larger masses. I don't know. Leave you with the question. With Aperitif, there's also an important cross match. I think at around 400 square degrees, but only 21. Remember, out of 2,000 are detected. They're only slightly more massive, brighter with a bit more of H alpha flux, but the redshift is similar. This is the VLA, I don't know what it stands for, but the high frequency survey. I just put a bit of the result, but only 5 of my galaxies are detected with very high stellar masses and high redshifts. And we move on to the precursors, yes. So I feel like I'm doing stand-up, only hearing laughs. So this is a continuum survey, and this frequencies, 2 bands at least. And this is the one that we were discussing yesterday that reaches very, very high declination, which is a huge overlap area with J plus DR3 and with the full J plus and J pass. And even big, even if you limit yourself only to 30 degrees. So this is really interesting. But again, only 13 matches. This is shallow. And in this case, it's really clear that it's only the brighter edge of the survey with the strongest H alpha flux, the detected one. So yeah, top 5%. Wallaby, it's the H1 survey, which would be very nice to cross match, but in the very small, area that overlaps, I only have 5, so no cross match. But if you take the whole J plus catalog, there's 1,700. So there's something could be done potentially with this. This is a bit of a summary of several of the surveys that I showed. And yeah, here there are the magnificent 2. There are only 2 sources that are detected from my sample, from LOFAR all the way to Vilas. And Markarian is very nice, very well-known galaxy, which is not this one, it's below, but there was a problem. Sorry, you're missing it. Oh my God. Is it a chat? Journal, huh? Yeah. Can I click on it? Ah! No.
The usual alarm.
Okay. But the other one, the green one that you were seeing there.
No, stop moving that because then I cannot.
This green one, sorry.
You are free to go.
This green one is a new one. It has not been reported, and it's really bright with a strong high mass, a strong star formation. I'm very curious because it seems like there's this is redshift 0.2, but there's like some extended emission over here. It's not just a blob, and this is detected in all the array, but this is the only one. And to finish with the expectations, this is a plot that again was shown yesterday. It has a name, but I don't remember now. But you can see that it is for the very low redshift. It's going to be great. I mean, the expectation of this very wide survey, which is, well, medium wide survey, it's enough to detect probably all the ELGs that can be detected in J+. For J-Pass, you can go probably a bit deeper, and you will have probably the medium would be best. So you compare at redshifts more like 0.2. Even if the area is smaller, you still get maybe 100 galaxies for each one of these proposed surveys. Of course, this is, again, no SKA time has been allocated yet. And this is for the continuum. This is also, it seems to me like with the MU precursors, it would be enough for most J plus ELGs. There are lines, I promise here, but that is the idea. And for the white tier, the white survey, that would be probably enough for the all ELGs that JPass can select. And I leave you this with my conclusions. Sorry about the extra time. Thank you.
Thanks for an interesting talk. Any questions? Yes.
Yeah, it was very cool to see all these cross matches you did. And so what I'm curious is, you've done this, it's exploratory. What do you think is the most interesting? Like, what are you gonna follow up after today?
Oh my God.
Spend more time with, like,
I'm gonna go to bed after today.
yeah, I mean, you did all this. Like, is there one where you're like, this is really cool, and I wish I had more data, or I want to follow this up? I think this is gonna be like the most fruitful path.
For now. And I'm not saying this because you asked, but alfalfa, I think it's one of the. I was looking for the coverage of alfalfa, and it showed a blog post by you from 2009 about the alfalfa. That was fun. I think that's the one that has. I was already trying to do some science with it, so I think that's the easiest and the fastest to do something. The others, there are very few selections, and also like I have no idea in mind as to go from flux in the lower band to science. Like that's a bit more complex. From what I've been understanding, what you really want is a spectral index that tells you the slope of the radio continuum. That's a bit harder to get, as you've seen. Like this one galaxy is nice, but it's one galaxy. So so that could be interesting as well. Maybe there's something weird going on. Why is that one showing up in all radio bands? But yeah, for me, the easiest path would be the H1. So I think there's the data release from which survey it is? The Apertive? No, Apertive is the
one with Vesterborg. Yeah.
That hasn't happened yet.
No, not really for H1. There's
exactly. Yeah. So that probably there's something there to when it shows. Yeah. Thank you.
Okay, Wendy.
Yeah, just to add to that, we've not really mentioned at all the other part of lo-fi is the low frequency survey called LOLS. It's at 50 megahertz compared to 150 megahertz. It's less deep than LOTS, so I see you get the most matches to LOTS because it is the deepest radio continuum survey at any frequency, covering the whole sky. So yeah, if you want to look at some radio spectral indices, you can, if you have sources that are bright enough. LOLS can also be interesting.
Okay.
Yeah,
Okay.
it might also show some interesting turnovers on the low frequency spectrum.
Okay. We'll have to see how that lost.
Online? Yeah. Okay. Okay. One question, Sandy. Okay. I cannot see
Who is Lourdes? Lourdes.
Okay, Lourdes,
Go ahead.
you can unmute.
Yes. Yes, Alejandro, I think it's great that you did the try to do some correlations and look at the data yesterday. That means that this workshop has been useful. Let me just give a small hint. I think it's something, because I've seen this before, when people not doing, well, I'm sure we do the same with optical data, but when you look at the correlation with alfalfa, be careful because given the size of the beam of alfalfa, you may be gathering the H1 of several objects, and you are comparing with the information you have in the optical for one object, and this will change the plot, right?
So thank you for the comment. Yeah, I've been showing here in this cross match, but there are many decisions involved doing those cross matches, and many can be the wrong choice, especially, of course, the radius of the cross match. But with alfalfa, I downloaded a catalog that actually had RA and DEC for optical counterparts. So I think I did that one right. And
yeah,
also,
but still you don't know. You can look at Jamie's book paper, which is the same, or I don't know if it's 2020 or 2022 that Amidou showed yesterday, where she was, or maybe it's another one, where she used alfalfa to study just the integrated emission of pairs of galaxies compared with isolated galaxies, and you find surprises. So just I understand that you didn't have to do that yesterday. That's not something you cannot do in a day or anything. But always be aware that you can be having some other object in the field, even if the main match in alfalfa is identified to be one galaxy. But for example, for Amiga sample, where we did gather the H1 spectra for 800 galaxies from the bibliography, we had to be very careful and not just trust the catalog, but revise one by one if there was some other object at the same redshift. The shape of the H1 profile is very telling. So if you have one galaxy and the profile looks very weird, either the galaxy is very, very disturbed or there is some companion. So these kind of things I think are useful if you want to just jump into the catalogs. And
yes, that's super useful. Thank you. Okay, let's thank him again, and we'll move on to the next speaker, Juan, and he's going to talk about the role of AGN jets in the evolution of galaxies with J-Pass, J+, and SKA precursors.
Okay, thank you very much. So this is a topic that I already introduced yesterday in the discussion. First of all, feedback is a very important ingredient in galaxy evolution because it's required to match the mass function of dark matter halos, which is the black line in the figure, with the observed mass function of galaxies, which are the green squares and the pink stars. So basically, dark matter halos are relatively efficient at forming Milky Way-like galaxies, but then when you move to higher and lower masses, the baryon physics prevents the formation of the structures. And in particular, at high masses, above 10 to the 11 solar masses, the dominant feedback mechanism should be related with accretion onto supermassive black holes in active galactic nuclei. So AGN feedback comes in two flavors mainly: radiated mode, which is quasars, so these are sources with a very bright accretion disk, or kinetic mode, which are mechanical feedback produced by jets in radio galaxies. Regarding the first one, the problem is that the observational evidence supporting the amount of feedback required by numerical simulations to reproduce the mass function that I showed before is not observed in large statistical samples. For instance, for bright cipher nuclei and quasars, which are easy to observe, the correlation between the AGN and the properties of the host galaxy do not reveal a strong positive or negative effect on the star formation of the host galaxy. So it's not clear whether this feedback is there and is producing the effect that the simulations require. Kinetic feedback has some advantages. First of all, it releases more energy than the radiative feedback. This is based on the radio continuum emission, and especially below redshift 2, the energy density per unit volume released by jets in AGN is much higher than the energy released by AGN winds. This does not mean that this energy is couples and is transferred to the ISM, but at least you have a large amount of energy that is produced by this mechanism. And a possible feedback mechanism is that you launch outflows by the jets, but you can also hit the circumgalactic medium around galaxies. So you have Cygnus A is a good example because you have the small optical galaxy in the center, and then radio jets that have produced these bubbles. But while these radio jets have been developed, there is a hot coronal gas bubble that has been inflated around the galaxy. And this isolates the galaxy and prevents accretion of new material that will form new stars. So in the end, what you're producing is the starvation of the stellar populations in the host galaxies. The advantage of extended radio galaxies is that you can study along the jet trail the different events that have been produced in the past. So, for example, this is a map of you can also map at different radio frequencies. You can map the shape of the spectral, the shape of the continuum, of the radio continuum, and you can identify, in this case, how 3 different regions along the jet, they present synchrotron emission that is progressively colder. So this is an electron population that that emits synchrotron emission, and the regions that it's located farther from the black hole, it's the less energetic, has already lost some energy, and the region closer to the black hole, it's more energetic. So by studying this for a large statistical sample, these structures, you can reproduce the past history of accretion in the central black hole and the duty cycle of the jet. What's the advantage of doing the match with the optical? That you can correlate that with the things that you can measure in the host galaxy. For example, if you take your photospectrum and you fit that with stellar population synthesis model, you can determine photoseeds, you can measure star formation histories, star formation rates, and stellar masses that you can correlate with the power that has been released by the jet and the past history of black hole accretion. And that will give you a very comprehensive picture of what is the effect that the jet produces on the host galaxy. If you do that for a large sample, then you will be able to match these two processes. And for example, one very interesting science case for this is the giant radio galaxies that have been discovered recently in low frequency radio emission, and trying to understand if the host galaxy in the center of these monster structures has something in particular to be able to produce this very extended radio emission. So now let's do some numbers. Do we expect to measure these galaxies in our surveys? In the radio part, the massive galaxies are very bright emitters at radio wavelengths. So this is the fraction of early type galaxies detected above a certain radio power versus the stellar mass of the galaxy. So you can see that above 10 to the 10.5, 10 to the 11, the galaxies become very bright in radio emission. So most of the massive galaxies are strong radio emitters. And you can also see that this is from RAX, Tier 1, but you can also see that in lots. When you look at galaxies about absolute K-band magnitude of 25 or 25.5, then the fraction of galaxies above a certain power is more than a half, up to 70 or 100% if you cut at higher luminosity. So massive galaxies are frequently strong radio emitters. And this is also because above 10 to the 11 solar masses, which is more or less minus 25 in absolute magnitude, the relation between the K-band luminosity and the power in radio is very steep. So it's above an index of 2. So that's why although the scatter is high, but the trend is that they become very luminous. It will be an asset to have also H1, and you expect more or less that for that range in stellar mass, you will have like 10 to the 9, 10 to the 11 solar masses in H1. And these are the numbers that FAST is measuring in the first pilot surveys for the nearby universe. So we will probably have also H1 measurements for these guys. So let's do some crude numbers. In lots DR2, there are about 700 sources per square degree, and a first estimation for J plus and J plus for galaxies with masses about 10 to the 10.5, we expect like 300 in J pass and about 60 in J plus. This doesn't mean that that all of these galaxies are resolved and extended, but with these numbers, if we have an overlap of a few thousand degrees, then I'm sure that it won't be difficult to build a large statistical sample of these sources. So now, if I convince you that extended radio galaxies are cool, I will try to convince you that compact jets are even cooler. And why is that? Because they are very numerous. So basically about 10% of the AGN population are radio galaxies. Based on their morphology, they are classified as FR1s or FR2s. FR1s have a bright core, and then the intensity decreases toward the radio lows, while FR2s have a relatively faint core compared to the very bright radio lows. So they become brighter towards the extremes. FR0s is a class that has been recently discovered, and these are essentially compact radio emission in the center of galaxies that has very similar properties when compared to FR1s. So the core is undistinguishable from the cores of FR1s. The difference is that these sources lack the extended radio emission. So they might be extended at a few hundred parsec scale, but they don't show the kiloparsec scale size lobe of FR1s. So FR0s, the advantage is that they are much more numerous. So essentially, about 1/3 of all the galaxies in the local universe are low luminosity AGN, and most of them have a compact radio source at the center. So these radio cores, they typically show a flat spectrum at radio wavelengths, and that means that they are probably young radio sources. And they can have, they are relevant regarding the feedback because they can produce a strong impact on the host galaxy. For example, this is a recent result for low luminosity AGNs in which there is a compact radio source in the center of these galaxies, and these compact jets are able to produce turbulence in the emission lines along the direction perpendicular to the jets. So the middle panel shows the oxygen-3 emission. This would be the narrow line region of this galaxy. The jet is aligned with that, but then the kinematics of the gas along the perpendicular direction is perturbed. This is in agreement with simulation of low power jets, because low power jets, they are not energetic enough to drill a hole in the galaxy and escape. So they collide with the ISM, and then they start to increase the pressure and to disturb a lot the cavities in the ISM. So in the end, they are much more efficient at transferring energy from the jet to the ISM, like 10 to 15% of the energy is transferred to the ISM. And they are way more numerous than when compared to brighter radio galaxies. So this is the luminosity function of FR0s, and so between powers of 22 to 23.5 in watts per Hertz, they are much more numerous when compared to FR1s. If we look at the result from LOTS, this is the radio power in the vertical axis versus the stellar mass of the galaxy in the horizontal axis. And you can identify here two main sequences. So the lower one is caused by star-forming galaxies, and then you have the radio galaxies in AGNs. Well, for FR0s, they dominate the region between 22 and 23.5. So they are at the junction between these two main sequences. They also have interesting properties. The host galaxies of these of FR0s, they tend to be early type galaxies, but for example, in white colors, they show very large spread. So some of them, they still have, they inhabit in galaxies that have star formation. And for example, this is a result from the pilot survey from EMU, in the figure I show the normalized counts. The red line correspond to extended sources, and the blue line correspond to compact sources, and the horizontal axis is the spectral index. So basically, all radio sources, the ones with a very steep spectral index, they don't show any difference between extended and compact. But when you look at the population of compact radio sources with flat spectral indices, the population of compact objects is much more numerous. And this suggests, so this could be produced by compact radio emission in FR0s, but also by free emission. But this suggests that going deeper in continuum is going to, so deeper surveys in radio continuum are going to reveal a big number of compact radio galaxies. And basically I conclude here. So the two main science cases that I think are very interesting for synergies between optical and radio are extended radio galaxies, where we can characterize the jet duty cycle and correlate that with the effect on the stellar population of the host galaxy, and then to understand what is the role of compact jets in the galaxy evolution, because since they are the most numerous class, the effect that they should have on the cosmic impact that they would have would be dominant. They should be the dominant class in terms of feedback in the universe. And that's all. Thank you.
Thanks. Any questions? Online or? No? Okay.
Just a curiosity, does the three classes of FR0, 1, 2 suggest some temporal progression or some?
Yeah, this is actually this picture. Well, it's not clear how is the evolution, because before FR0 came, there were compact radio sources, compact gigahertz peak sources. And so these, the evolutionary models connect the bright compact sources with the FR1 and FR2s. But FR0s are much more numerous than these and these. So it's not clear if these guys, they come here and then they evolve toward this, or, but still a large fraction of them don't make it because the numbers don't match. So you have 5 times more FR0s than FR1s. So that means that those jets, they cannot develop, they are destroyed, they are, it's one of the things that are under debate right now.
Okay, let's thank the speaker again. We'll have our first online speaker. I don't know how this works, but
So, Ivan?
Yes, can you hear me?
Yeah.
yes, yeah,
Perfect.
Yeah, you can start whenever you are.
Okay, let me share the screen.
Sure. Yeah.
Can you see my screen?
Yeah.
Perfect. Hi everyone, my name is Iván López. I am a PhD student here in the University of Bologna. And sorry I didn't make it to go to Spain. I have some immigration problems, so I cannot leave Italy right now. But well, I want to try to convince you that low luminosity AGNs are important. And after the talk of Juan Antonio, I don't think I can, if he didn't do it, I don't think I will. But I will focus more in the accretion on low luminosity AGN instead of the jet that is the thing that he just explained. Just to start with a broad picture, like a standard AGN will produce emission in all the wavelengths. So the SED that we will see goes from radio to X-ray, and in X-ray, like the emission is coming from the corona, the hot corona. In the optical UV, the emission is coming more from the accretion disk. In the infrared, is coming more from the remission of the toroid. And in radio, there is a huge discussion. In radio loud AGNs, we can say that it's the jet. And in radio quiet, we say that it's a wicked jet or just synchrotron emission from the center. So a popular topic in the field in the last years is the AGN host coevolution. And basically is that we think that the host galaxy evolved in a way that is linked to the black hole, supermassive black hole growth. And we have evidence about that. The first one is the scaling relation between the mass, the black hole mass, and the host galaxy mass, the stellar mass or the bulge mass. Also, there is some relations between the derivative of these masses, so the star formation rate and the black hole accretion rate until redshift 2.5, so cosmic noon. And also, as Juan Antonio just explained, AGN feedback is using to suppress the star formation and to get galaxy masses that make some sense with the thing that we observe in the cosmological simulations. So what we did with mini JPass in terms of the coevolution, well, we grabbed sources that they were detected in the X-ray. We match it with the JPass. We also get some data from WISE and Galax. So we have like a multi-web approach, and we fit this the SED of these sources, and we study like the black hole masses, the black hole accretion rate, the stellar masses, and the star formation rate, and we model some possible scenarios for coevolution in the past. But when we try to understand which population we were studying with this approach, well, you can see that my histogram of the Eddington values is lacking any sources below -3, right? So below -3, we enter in this universe of low luminosity AGNs where the accretion is relatively inefficient. Let's say that the SED fitting codes, the most popular that we use, that is Sigale, usually assume that the accretion is by a quasar mode, right? So that means that the X-ray emission is linked to the UV optical accretion disk that usually has this shape of like the big blue bump. And for the accretion, the model is like the standard accretion disk, thin disk, that maybe is not true in low luminosity AGN. So we start to develop this new model that is particular done for low luminosity AGNs. So let's say that in a low luminosity AGN, the accretion, we can have like the typical accretion disk, but at one moment becomes not stable anymore because there is no enough pressure to keep it, and start to have like advection dominated accretion flow. That basically means that it's not the same SED that we have for the standard accretion disk. Of course, we can have jets there, but I will not focus on that until the end. But basically, the big change in the SED is that while the quasar mode is like a sum of different black bodies, for the ADAFs, we have a synchrotron emission, Bremsstrahlung, and inverse Compton. So you can see here in the right, while in the gray shape is like a typical quasar mode for a particular galaxy. Particular black hole mass. The other lines are different ADAF solutions for exactly the same black hole mass. So you start to see that the shape is completely different. So in our approach of this new module for Cigale, we are changing the seed photon, so the central engine now is like an IDAF and a truncated disk. So you can see here in red, it was the previous parameterized version of the accretion disk from Cigale, and here this is like our parameterization that follows the work of Nemen 2014. And these different bumps here are the different accretion disk relevance compared with the continuum of the ADAF. And we are changing the X-ray prior, because before they were using this connection between the X-ray corona and the big blue bump, but you can see here that this is more optical UV, and the bump now is in like more infrared. So we are using the works of Asmus 2015, and that Fernández-Ontiveros also proved that it's working for low luminosity AGN. So we are using the X-ray and infrared connection. I think I want to say here is that these blue shades regions here are other two regimes that we are not working. That is the X-ray, because the X-ray module and Cigale we are not changing it, and the other is the radio mode, the radio region that I will explain a little bit how it works in Cigale in some slides. So with that, we are fitting 50 local low luminosity AGNs that they have like X-ray detection. We did a photometry from using this X-ray data, and we did from the UV to 250 microns. And now we are recovering finally Eddington values that they are even, you can see that they start at -3, that they were where we have the problem before, and goes until -7, right? So now we are in condition of like start to think in like these two different modes, and start to try to study the demography of a black hole from a SED fitting in a different way. A great combo that we can use is for sure Rosita as an X-ray prior and the JPass in the optical. But there is life below 10 to the 12 hertz. And this is like the thing I want to start to discuss here, because these are the solutions that we are using from Nemen. We are centering in this part the green shaded area. But the radio, usually characterized by the power slope, has can have different slopes for the ADAFs, and you can see here, while the green dashed line is the ADAF, can also live with a jet that is the dotted line here, right? So these sources can also have a jet in their SED that we are ignoring for now, but can be a very good add thing for future modules for Cigale. So right now, the radio Cigale mode model the star formation radio emission from correlation with the infrared and using a slope. And the AGN radio emission, there is a model that was developed for radio loud AGNs that use the 5 gigahertz emission luminosity connected with the UV, and assume another slope for this emission, right? So if I need to start to think how we can adapt this to the ADAF, well, we can just take different slopes that we have from the ADAF models, and this I put it for myself. I need to double check that the relation with the UV is there for low luminosity AGNs, because the emission in the UV is completely different for these sources. So now I want to start like a discussion about this type of things, because basically I think like X-ray gave us a very good solid ground to work with the AGN tomography above 10 to the 42 hertz per second, and get this black hole accretion rate density until cosmic noon. And from there, like the AGN coevolution model start to build. And one of the main problems that it has is like the obscuration, because we don't know the demography for obscure sources, and the host galaxy contamination for low luminosity AGNs, because you can start to have different problems from binaries, for example, that doesn't allow you to model, like to get this population of low luminosity AGNs. On the other side, the AGN feedback mode, at least the radiative mode, is the one that is inside the cosmological simulations right now, and seems that it's a key for the coevolution scenario. But also radio did a lot of things in the last years, where like we just saw the impact that you can have from a radio shed in the ISM, different spin measures, the jet-driven outflows. So right now, the AGN feedback in the kinetic mode is being tested to be incorporated in the new generation of new cosmological simulations. So we will have the result about these two modes in the future from the cosmological simulation, but it's very interesting where we are going, right? But not only like high luminosity feedback is there. So we know that the low luminosity AGN winds have the energy enough to suppress the star formation in an already quenching galaxy. So basically keep the galaxy suppressing the star formation after other event. So this is very nice to like keep in the local universe the galaxies that maybe for mergers or for other things are already quenched. We know that the low power jets can get trapped in the host galaxy and hitting the ISM from simulations and also some observations. I know that people is working in hydrodynamical simulations for the study of these ADAF winds right now. So also like in the next years, we will have a lot of results about these ADAF winds. In particular, we got some data from BLA, JWST, and Chandra to resolve the impact in M58 in NGC 4579 to resolve this dichotomy between the ADAF and the jet, because there is evidence that there is an ADAF, there is evidence of there is a jet, there is evidence that the star formation is suppressed in the center of the galaxy, but we don't know which blame, right? So we will have enough Chandra resolution to get an UFO that is producing like basically an outflow of a very high velocity that is produced by the ADAF. We have a good resolution for the jet, and we will have a resolution enough to resolve each molecular cloud in this galaxy and study the particularities of the low luminosity feedback there. And there is also the project of reveal low luminosity AGNs that will have JWST data for other 7 low luminosity AGN sources. But all of this is more like some approach from the theory, from some observations. But we know that the supermassive black holes spend the most of their time being inactive or at low Eddingtons. And we know that it's huge, the population of low luminosity AGNs in the local universe. But to understand the real impact of this feedback in the and compare it with the kinetic mode and the radiative mode in the high luminosity sources, we start to build a low luminosity demography. So right now, we think that maybe this module of Cigale can start to do that. Basically, that start to say that we need to start to work with eROSITA and JPass soon. But also radio priors, instead of only like X-ray priors, can help to constrain the demography. So I am thinking that in the same way that I am using X-ray to try to to give a prior for the optical UV that is completely contaminated by the host galaxy, we can start to do it from the radio also. Even more like JPass and SKA mid, we can like start to study the existence of the low trapped jets in these sources and try to constrain if there are jets or ADAF driven feedback, right? And in particular, I think JPass has a very good opportunity here because we can also get BPT lines and BPT diagrams, and particularly we can resolve especially these BPT diagrams. And I saw in the first day that this galaxy 5055 is part of the galaxy that the JPass will observe first. So we can start to do some testing there because that's an X-ray detected liner. Sadly, we don't have a radio, or at least it's detected with the Merlin in this galaxy. But at least to start to discuss if the BPT can work there, we can have a very nice resolve diagram there. And also from the SED fitting, we can constrain very well the host galaxy parameters like the black hole, the bulge mass, the star formation rate, and the star formation history. So basically, this is the end. I try to convince you that low luminosity AGNs are important. In the short future, we can start to test Cigale, the new module with the X-ray and JPass, and try to get a demography of low luminosity AGNs. For the future, we can start to use radio priors to improve our SED fitting, and that will help to improve our demography and also study the X-ray biases that we will have because accretion is also there. And for a long future, we can start to see to have a detailed view of these sources and try to go from smaller samples to large samples of sources to study the low luminosity feedback. But my short future is writing the thesis because I need to submit by January. So right now I'm not having new projects, but after February we can talk. So thank you.
Good luck for the thesis writing. Any questions? Yes.
I want to ask you. You said the agent is tested in the new cosmological simulations. So what is in the new cosmological simulations you mentioned? And is it developed? Is it made by the Eagle Group? And do you know how they add the agent feedback to the new cosmological simulations?
So right now, I know that Colibri, that is, yes, the new version of Eagle, is working on that. I know that the magnetic CAM is also adding a black hole spin and launching jets from there. I was talking about that.
Thank you.
Yeah.
Hi, Ivan. Really nice talk. One question about the module for Seagull. Do you plan to distribute that with the normal Seagull distribution? Is going to be an extra module with the normal Seagull?
Yes, we are working with I'm working with Yang, that is the person that did the X-ray model. So basically now you can choose between the previous model that will be called Yang 20 and my model that will be called López. So yes, you can choose at the beginning and will be distributed in Cigale. Yes.
And one short question: which ADAF parameters do you think you can constrain better? Which are the main ones that you think it's are going to be well constrained by the fitting?
So right now I'm just focusing in the luminosity, right, of the accretion disk that is not an accretion disk anymore. So the accretion luminosity, let's say, and with that trying to get an Eddington value. I will not. The model is not powerful enough to try to constrain like a transition radius or viscosities because we are just getting the shape of the emission, in the same way that Cigale was using that for the big blue bump. They were not fitting a black hole masses from the big blue bump, right?
Okay, thank you very much.
Okay, we are running out of time, so let's move on to the next online speaker, Benito.
Can you share the screen, Benito?
Yeah, I'm sorry.
You can just start when you're ready.
Okay, can you hear me fine? Everything?
Yep.
Okay, thanks. Yeah, so Benito Marcote. Would like to thank the organizer for this nice meeting. I would have loved to be there, but yeah, because of other restrictions, I couldn't travel there. So at least I can join online. In this talk, I will try to tackle another topic that has been not that covered that much, that is the transient sky and the combination between what the synergies between optical and radio. So, and especially with the very high resolution VLBI radio observations. So I haven't been able to be there, so let me do one slide of who I am, because for many of you, I'm quite outsider. Did my PhD some years ago already in the University of Barcelona on high energy galactic binary systems. And I've always been working on transient phenomena. And I've always focused from the radio part. So I come from the high energies, but actually from radio observations. And actually I'm halfway between galactic and extragalactic astronomy, because one part of my job is doing high energy binaries, and more recently even a follow-up of novae. And the other part of my work is in completely extragalactic, so fast reversed and gamma reversed that I will detail later. So actually, I have the synergies from both sides. And currently, I'm in the Netherlands working as support scientist of the European VLBI network, and working at JIVE. So actually, I would like to introduce the European VLBI network, the EVN, because this is a network of different radio antennas, mainly in Europe, but actually we cover other places, other continents, from Asia to South Africa, and actually we can combine with other networks in America and Australia. And then we actually combine, we correlate the data at my institute in the Netherlands. So why we do such a broad network of antennas? Because then we can recover a much higher resolution than other instruments. So we observe in the range of the gigahertz radio frequencies, mainly between 1.4 and 40 gigahertz, or 21 and less than 1 centimeter. And with that, actually, we can have a much higher resolution. So our observations typically achieve resolution of the order of 1 millisecond, that for most of the galactic objects, we are talking about spatial sizes of the order of the astronomical unit. And if we go further beyond our galaxy, we are talking on scales of parsecs, even at redshift of 0.1 or 2.1. So actually, with these images, we can really deep down into the inner parts of the systems that you may want to explore. And this is the most sensitive VLBI network right now. And actually, we are preparing all the path for SKA. Most of you are aware of the SKA standard observations with the MIT in South Africa and the low SKA in Australia. And actually, we made sure that even when the SKA will start observing, we will be able to integrate the SKA, at least the MIT, into the VLBI networks that we have all over the world. So actually, we will be able to put these antennas as extra antennas in our networks, and then make an interferometric array that still have baselines of the order of the Earth scales. So the resolution should be similar to what we already have in the EVN, but we will win a lot of sensitivity once SKA is in place. So for that, we will mainly combine most of the core of the SKA in South Africa, and then we will still use some of the antennas across Africa as new antennas. And then the idea is that we will combine all the data. So we have the benefits of SKA plus the benefits of VLBI, much higher sensitivity and resolutions of the order of millisecond. Then first, you may wonder why in transient science we do here, why we are really focused on the radio domain. And this is because most of these systems emit non-thermal emission, and this emission actually ranges in almost all cases from radio to X-ray, very high energy even. And the particularity of radio is that as it's a non-thermal processes, qualitatively speaking, just roughly speaking, we have a power law emission. So we will have a stronger emission at lower frequencies. In many of these systems, for different reasons, because I will be talking about the galactic binaries and also extragalactic environments, at some point we will have absorption because of the medium, depending on the physical parameters there. But roughly speaking, this absorption starts playing a role below 1 gigahertz. In some cases can be 100 megahertz, in some cases can be 10 gigahertz, but of the order of magnitude, we have for many of these sources peaking in luminosity on the order of the gigahertz. And that's why we really have a lot of observations focused on this radio domain. Of course, this also is because this emission is completely tied to the one that we observe at high energies. But here we have a much better resolution, so we can go deeper in sizes. So first, let me start with our galaxy. Alessandro already gave before a really good talk on accreting binary systems. Actually, here I will talk about other type of binaries, the ones that do not accrete, but the ones that have wing collision. And this was a really good example where the first observations were in the infrared and optical, and then we combined with the radio domain to really clarify this source. So this is APEP, a source discovered a few years ago. You see with the red colors in the left, the infrared emission. And this is around 20 arcseconds in size. So you saw this plume of dust with a spiral shape there in infrared. Then you see a bright, really bright star right in the center. So it was clear that probably this was a binary system. And actually we needed a optical spectra to try to resolve and understand what was the stars creating this spiral of dust. And from there we saw that they were likely two Wolf-Rayet stars. So actually this one became as the first putative binary system containing two Wolf-Rayet instead of only one with another companion. But it was only when we conducted VLBA observations when we actually resolved, this is the real image in the blue color, the radio emission. And as you may see here, this is kind of a bow-shaped structure that is indicative that here you have two massive stars, as we already knew from the optical. But actually what we are seeing here is the collision of the two really powerful winds, because we have two Wolf-Rayet stars, really massive and with really fast winds. And thanks for the combination of this image, so we can narrow down where are the positions of the stars, plus the optical spectra, we could really confirm that this was a colliding wind binary with two Wolf-Rayet stars. This is not the only system of this kind, and actually I trace other systems that produce even higher energy. So the so-called gamma ray binaries, where you have the same mechanisms as here, but instead of having two massive stars, you have a massive star and a compact object, likely a young neutron star. And in that case, you have a strong collision between the stellar wind and the relativistic wind from the pulsar. So phenomenologically, it's similar to this, but of course you scale up the energies. And in all these systems, the optical is critical to really understand what's the companion stars in there. trying to resolve where they are. And then from the radio counterpart, we can really narrow down and see what is the non-thermal emission, where it comes from, and what's the processes that are taking place there. This is the galactic part. Then I will go into two systems, first gamma ray burst and then fast reverse. So I will not really need to introduce too much for the first neutron star merger, the gravitational wave 1708-17. That was the first one detected by the LIGO Virgo systems. And then later on was associated with a short gamma ray burst from the Fermi satellite. So after the event, of course, there were a huge follow-up, first in the optical and other wavelengths to try to understand the host galaxy and then identify the kilonova and traced the kilonova expansion. And that was what traced all the properties from this merger. But there was one that was still a bit unresolved and took almost 1 year after until we clarify. And that was thanks to the high resolution radio observations. So in radio, in general, everything goes much slower. For us, we didn't have interest in the first days of the event. We actually had to wait until 150 days after the merger and when the radio emission peaked. So you see the light curves here, and then for us, the higher point was more than 100 days after the merger. So what we saw in radio is the afterglow, what happened afterwards and what was thrown into the space. And then still there were two competing ideas that all the optical X-ray observations couldn't resolve. If we have like the cocoon expansion, the shell after the merger was going outside with a much slower velocity. And then during the merger, we know that a jet-like structure needs to be produced. But then we didn't know if this jet had enough power to cross the cocoon and then propagate further beyond into space, or actually crash into the cocoon and then just reheats it. So thanks to millisecond resolution images, we could actually almost right after the peak emission, we saw this tiny, quite dim structure here. And at this resolution, we could actually resolve it, barely resolve it. So on one hand, we saw proper motion, we saw the superluminical motion of this afterglow, and also we saw how it was expanded. So with this, we could really confirm that the jet actually crossed the cocoon, and it was like a structure jet. It's not like one model where you have a similar density through it. So this is where we needed optical from the beginning in kilonova, and then we need a radio afterwards to resolve the details about the afterglows. And this is not the only case. Now we have the other kind of gamma ray bursts, the long gamma ray bursts that are just from the collapse of a really massive star, but phenomenologically afterwards is equivalent, let's say. Now we actually trace for the second time ever the expansion of one of these afterglows here, which is still just emitted. You see there. And if you detect the gamma ray burst, you already have the information after that, the localization and the properties, the optical properties for it. But in some cases, we do expect that there are some so-called orphan gamma ray bursts, which are the ones that we, for any reason, we didn't detect the gamma ray burst. So actually, we don't have the information from the first part of this diagram. Only from the radio part, we see a variable source, and monitoring it with a cadence of years, we can actually unveil that this is likely to be a gamma ray afterglow. And this is what happened in 2019. We think that we observe an orphan gamma ray burst. And this is the idea where we can actually do the opposite. In radio, we unveil this afterglow, and then later we really need the spectra of the region from the optical to really understand where it was produced. And then with that, I will go for the final part of the talk, which is fast reversed. This is a quite recent topic. it's only a 15 years old field. Fast reverse are really fast flash of radio light. And when I talk fast, so when I say fast, I mean that the burst only lasts for 1 millisecond of time. And so far has been only observed at radio frequencies. So in the last 15 years, we've discovered 1,000 of them, and we still don't fully understand what they produce, these bursts, and where they are produced. We know that they are extragalactic, coming from redshift on average of the order of 0.1 to 1, but still we don't fully understand where we can find these ones. We think that most of them may come from really young magnetars, but then we need something else to explain such luminosity and such behavior. So in the last years, we actually monitored fast reverse with the EVN, and we were able to really precisely localize a few of them. And actually, we discovered that the environments where they are produced were quite different. So from the first one that we discovered on the left, this was a fast reverse that is produced well within a star-forming region of a dwarf galaxy. And we know now that many of them are actually tied to star-forming regions, but not all of them. In the center, you see a fast reverse that is in a spiral galaxy, similar to the Milky Way in size, and it's actually really close to a prominent star-forming region. But actually, the fast reverse comes from right outside the edge. So you cannot actually blame an object that was just recently produced in that region. And the last one is a global cluster. So we discovered this FRB well inside the global cluster associated with M81. So from here, you can see that these localizations really were tied to the optical domain, because from the radio, we really have the high precise localization of the burst, but actually in all of them, the optical observations and spectra was key to understand what was the regions where the FRBs were produced. And with that, actually, we'll just go to the final slide with the conclusions. I hope that I've seen you why from transient science, actually, we are really interested on covering the full domain from radio to optical, X-rays, and high energy, very high energy domain. The EVN is leading pathfinder on the SKA VLBI observing modes, and actually we are in preparations to keep this already online from the beginning in SKA. And in all these sources, either the galactic or the extragalactic ones, having really a high precision or high resolution spectrum or well understanding of the optical environment is key to put in context the radio domain. So with that, I will finish here. Thank you.
More questions online or here? Yeah, I can see the online. Yeah,
That is one online.
okay. Just speak, please.
Hi, so Benito, are you aware whether the SKA VLBI will be available at, let's say, any time, or there will be specific sessions when SKA in VLBI mode will observe? Is there any news regarding this aspect?
Well, the constraints will come from the other VLBI networks. So to get the SKA VLBI, you will likely to need to apply for what you do now for one of the VLBI networks and including the SKA. So of course there you will be tied also to the time of the VLBI facility that you apply for. From the SKA, they will evaluate the proposal similar to what happens in the global ones. Like you may have different networks, and then they have local TAC committees that they will evaluate. For the SKA, in principle, they observe 24/7, let's say. They have less restrictions in time, the proposal, but then the main constraint there it will be from the VLBI network. If you apply for the EVM, for example, you will be tied to the observing sessions that we have. And if it's from the LBA in Australia, it will be similar case. So everyone will try to do efforts. Still, that part is not completely talk, of course, or clarify, but then that will be likely the idea.
If may I ask us another thing, or well, okay. Then.
Yeah, sure. Go ahead. Yeah.
So the other question is regarding is the availability of the data. Will be only the, let's say, VLBI mode data that will be available for the user, or also, let's say, the rest of the data, so one could get an image, let's say, of the diffuse emission of the galaxy, host galaxy, or anything for those transients or whatever. Is there any?
Yeah. Sorry. Yeah, you will have different modes, observing modes. That will be completely feasible. Of course, depends on how much the rate you have, but then you will have different modes at the same time of the VLBI that will go and integrate to the other ones. You will be able to have the SKA, probably not full bandwidth if you take part of the bandwidth there, but actually it's not that constraining because the total bandwidth of SKA will be much larger than the one that you will use. So at the same time, you will be able to have the imaging from SKA. And even if you are interested in other modes, like let's say pulsar, timing mode at the same time, you can actually do compromise and get all those ones at the same time. So similar to, for the user, equivalent to what happens with VLA and VLBA, or in the past, Westerbork EVM. Like you may have the other ones in parallel.
Benito, Alessandro here. As a fast radio burst illiterate, is there anything that has been done or can be done in other wavelengths other than radio? And more specifically, is there anything that we with JPass or J+ can do?
Yes. So,
millisecond timescale.
Sorry, say again the last bit.
Go up on a millisecond timescale.
On millisecond.
Yeah, they cannot follow up on a millisecond time scale.
Yeah, no, okay, yes. No, one thing is the burst emission that takes 1 millisecond and that's it. But we know that there is nothing else associated to it. So the interest, unless you go to X-rays or really fast optical imaging that you may be interested to search for bursts, the rest of the interest is on the continuum images that you have in the region. So our main constraints actually, now that we are getting way much larger number of localizations, is having good valuable optical data on the regions, on the host galaxies and the spectrum of them. So when we had 1, 2, it was easy to ask for time in many of them. But of course, that comes trickier afterwards. So having good quality measurements of the host galaxy within a survey that is covered or in those ones, either before or afterwards, will be critical when we move towards the tens, hundreds first reverse localizations. So the idea of the optical and other wavelengths is to have actually the continuum emission, nothing to do with the burst. Like in the galaxy that you have, having a spectrum of those ones and then trying to understand what's the properties there.
Thanks. Okay, let's end the morning session and let's thank the speaker again. So now we will have a break and we will come back at 11:30 for another discussion session. 11:30.
Okay, so we're ready for the last discussion session, which Carlos and I were put in charge of. Yeah. We talked a little bit about this. I put together a couple of points this morning, and then we'll see what else happens. Since I'm doing it, I'm now coming from the H1 survey side. This is what you do. You do things that, you know, your personal interests. And I think I want to talk about this a bit. I mean, also had a great discussion yesterday about like the JPass footprint, but I don't think we need to revisit that discussion. And we can move on to a new discussion. And in fact, but let's talk about another footprint to start this discussion, which is the aperitif imaging service. So my role is I oversee a lot of this, and right now I'm sort of overseeing some of our data processing, and then as part of a team that's led by Rafael Morganti, working on some second generation processing and doing improved things. And so I think I wanted to, highlight the survey coverage and also talk a bit more about our plans and understand if there's things that we can focus on or prioritize in our planning that would maximize the science return by having synergy with JPass and JPlus, which I think would be great for all of us. Okay, so this is our survey coverage footprint, the way I plot it. Where a colored circle means that we have observations on that field, and the color coding is just a visit. So pink are things we visited twice. Blue is a single visit, and then there's a few green circles, those have multiple visits, between 8 to 10 visits. And to the best of my eyeballing abilities, this is mini JPass. So you can see it does fall within our footprint, and we can sort of, as it grows in this direction, we'll have coverage on it. And so we've released some data. As I said before, it's data that's maybe not like what you're ready to do science with right now. And we're working on future data releases. So one of the things we're working on is work that's led by Tom Osterloh and Alexander Klutman, is an improved continuum imaging pipeline that has high quality continuum images and then releasing nice mosaic images and source catalogs over regions of the sky. We've done that for a couple of deep fields and planning a couple more. And so one of the things we've discussed, and I think I might take back from this meeting as something that we should sort of set when we finish the deep fields we're doing. We've done Butase, doing Lockman Hole is almost done, Eliason 1 is done, and we're going to do Goods North. The next natural one to do, I think, is to do the Goth Strip region that we have, and that would be really helpful here. Now the other thing I think, and then eventually we want to, of course, apply that processing to our whole sky, but we've been focusing on these few fields first, thinking that we can, again, maximize science return. Like I said, the Butase one is public, the others are coming, and they come cross-matched to LOTS already. So you have your association with your low-far radio source, and LOTS has very kindly done the association with the optical counterpart, so there's, lots of information there. The other thing we talked about is the H1 aspect. So there are lots of existing H1 data products that Kelly Hess has made. They're a bit scattered over the sky, but they're available, and we can also do limited things upon request, and for specific proposed projects and such. Something I have been thinking about from this meeting is that maybe it is also useful to do something similar, like focus on this region of the sky, and try to say, can we take a couple of pointings and make like a nice mini H1 catalog or something, and maybe that is a good way to sort of get us kickstarted on some H1 data releases and also generate some science through the connection with JPass. So I don't know. Zero promises on any of this. I'm not telling you how people strapped we are for Aperture. And so continuum stuff like a deep field image here or there, that could be early next year, potentially, or mid next year. And we are planning to sort of release all the data products we have by summer of next year, but those are the ones that it's just like cubes and images and you have to do a lot of processing yourself. H1 data products, I think the timescale I'm talking about, other than like requesting specifically something for a small project, is probably 2025. And there is, like I said, zero promises, but I do think I see a lot of interest here. So there's this part, and I guess sort of the discussion is to hear what you would like, what you would be interested in. And if there's other, I put this star on, should I have other stars on this map that I should be thinking about? Anything?
At least in J+, we observed the Lockman Hole on purpose, so we already covered that. So
so
for sure we have that in that region. And I'm not sure what is the size verification. It has SV. I don't know if it's
a little bit to the left.
Or is
to the higher.
It's around 7.
Okay, and I guess I should try to point to things with the maps on screen to be inclusive for online.
I cannot see the number.
So this is 16 hours here. And then this is 45 degrees. I don't know where, so I'm at 16 hours and 45 degrees. Where do I go from there? Okay, so it's great to hear that J+ already has Lockman Hole coverage. Like I said, I know the processing of high quality continuum image processing is being done right now. We're very close to finishing that, and that should be out early next year. So it's great to know. To tell all of you that will be coming, so please use it. And to hear that there's people who will be looking forward to that data.
So, Betsey, I'm not sure if you mentioned, you're talking about deep fields, we also have the LOT survey deep fields. So that goes significantly deeper than the line area survey. So Lock and Hole is one of them, Booties is one of them. Where we got, okay, there's deep optical data as well, with like 98% matches between the radio and optical in those fields. The 150 megahertz continuum.
Yeah, so I guess this was in my head and I forgot to say it, so thank you, Wendy. When I say the deep fields I'm talking about, they're not deep for aperitif, they're our normal pointing. They're the low-far deep fields that we're doing first to cross-match to. So when I say we cross-match to low-far, it's not just the lots, but the deep data is available there too. And some of them at least also have do they all have the low frequency also? So it's not just HBA, but LBA.
No.
I know Booties does, because I know we've done that, and that might be why we did it first, actually.
Only Booties does, the rest are coming.
So it seems that the current data are there in the pointing. So you already managed to reach the JPass observations. Are there 16 hours, 45?
Okay, so I found them and we don't have any coverage right now.
Yeah.
Okay. So I had one thing right and something else wrong, in a sense. Okay. Oops, I wasn't ready for that discussion.
Also, we have the JNet that I'm not sure about the location.
It's too far. Well, not necessarily.
Here?
Let me get in decent units. 17 and a half hours. Just about.
Yep, nope, that's not happening for us.
The Stefan Quintet seat already has some observations too. Where was it?
Oh,
It's 22 hours more or less, and 20 degrees.
yeah, getting there.
Oh, 20 degrees is not, we're not that far south. Where do we go? Just
We are
below.
very good.
Yeah.
Not overlapping each other. In some.
So I'm just gonna be happy with my nice beautiful black star then. And hearing that like you also have long pole coverage for JPass.
So the JNAP is at 17, 22, and 65.
Yeah, we don't go past 16 and a half in right assumption. So.
How come?
Why did we do that originally? I think it was mostly maximizing, so there were some scheduling constraints. It was, we wanted to stick here, well, we were a little wrong on where HETDEX was, but where HETDEX was and some other multi-wavelength coverage. So we just sort of, yeah.
Basically, you have a seed like kind of reasoning.
Yeah, but we didn't use seeds in the same way. But yeah, it was, we sort of had to limit our footprint, and then we just say, like, for the science we want to do, you know, what's the data that sort of matches with the most. Yes?
Yeah, for doing this in a more, I don't know, formal way, it would be great to have multi-order coverage mock maps of this. I mean, not right now. Right now, all we can do is that, but to do the cross matches, it's really helpful. I don't know if you have them.
No.
I haven't
just a sec.
I've been looking for them, but I haven't found them.
If there aren't, it's easy to create them. I can do them.
Well, I mean,
Where is, I have to just find, this is what I'm looking for, to share that screen, and then, you mean like this?
Oh, yeah, oh, sorry.
Yes. I don't know if blue means that you click it. There is something there.
Yeah, I don't know either. I'm pretty, I mean, so I know that the aperture data release one, like this coverage map, or I don't know. So I'm not super up on the VO stuff, but like it's in Aladdin and you can find it in things. And so this is the data release one hits with mock. And yes, I don't, yeah.
Yes, it is.
But is that the whole?
So it's not the full survey coverage because it's so it's for my first year of observing, but it actually, because it's just the first year of observing, like we fill in more around it. But you can, this isn't the best view, but you can sort of see, like this gap here gets filled in and stuff. But it gives you, like, first order, a sense of, you know, if you assume that some of, like this gap gets filled, this gap gets filled, this between these two parts does not get filled. But like it gives you a sense, and I think so we're working towards the second beta release that'll be all observations. We're aiming to do that by summer next year when we've done our first generation processing. And so I mean, I'll take it, and I assume we'll do something like this for that, but I'll definitely take it with me, hopefully, if I don't forget that we need a mock to go with it. But we have a lot of people at Astron who care about this sort of thing. Like it's their job to ensure good data VO standard thingamajiggers.
Right. And what was the idea is that aperitif is done, so.
Yes, so we're completely done observing. We've been done observing for more than a year, and yes, we are still processing the data.
Yes.
But so what that means is like our footprint is completely fixed. The only thing that happens is sometimes I realized there was an error in my like notes or tracking of things, and an observation that I thought was successful was failed. So we only lose coverage at this point in time. That's only happened like once to one field. It's okay.
Okay. So there is no way to fill the.
No, so there's no way to fill those gaps with data from accuracy. Yeah.
At least there is open time that you can ask for, but.
No, so like accuracy is completely decommissioned.
Okay.
Yeah. So if you want, H1 observations, you're not proposing to best of work or accuracy. You can propose to VLA or Meerkat.
Okay.
And if you're looking at things that are further south, the Meerkat has open calls as a reasonable mapping facility. It says actually it's pretty good survey speed because it's so sensitive.
Okay.
Okay. Anything else? Because I think I took a few useful pieces of information away. How much I'll be able to action them, I don't know, but I always have big hopes of what I will do, right? Okay. So then I had another point I wanted to discuss, and because I'm making my life complicated, I have to like reshare because I'm just sharing an application at a time. Come on. Yes, I know people can see my screen. Let me do things to my screen. Okay. So the other thing that I thought would be, from my perspective, a little interesting to discuss, because I had an idea of the answer, but was not 100% sure, is the idea of H1 stacking and the JPass redshift accuracy, and whether or not it would actually enable it. And I think my gut feeling is kind of probably not, but I thought it was worth asking, since one of the big things that JPass will do is these really accurate photo Zs with this really great filter set. And so this is an example from work with Automatics did a while ago, looking at taking sort of a template spectral profile that has this shape here you see is the strongest peak, and then basically doing a stacking experiment where you added different errors in the redshift. So starting with no error, which is the nice tall peak, to up to 250 kilometer a second error, which is your sort of really smeared out peak. And the point of this is just to sort of give a sense or a handle on how accurate your redshifts need to be for an H1 stacking experiment, because as you have less accurate redshifts, you're not aligning things optimally, and so of course one thing you lose is the ability to say anything about the width, the intrinsic width of the line, or the line width of the sources you're measuring, but you can still measure the flux. But as your redshifts are less accurate, you need to stack more and more things to achieve the same signal to noise, which is what this plot shows, and she has some other example plots. And so and how this accuracy also is correlated with what you actually think the width of the line is a bit. If the lines are narrower or broader at higher redshift, then that could change these constraints a little bit. But I guess I thought I'd give a sense, show this, what do people think they'll be achieving with JPass? Do we have a hope of doing this? Would it be interesting, or do we just say, no, we're still gonna stick with spectroscopic redshifts for stacking? Yes?
250 kilometers per second,
Yeah.
the other one is still too optimistic.
Yeah. And so then the question is, okay, so we have a bigger error, but do we get enough galaxies by using photo Zs rather than spec Zs that we just say, okay, well, rather than co-adding 1,000 spectra, we have to co-add 10,000, but we'll have 10,000, I don't know, I haven't done those numbers, I just thought it was an interesting thing maybe to think about.
What about galaxies with PDF for the photometric redshift that it's narrower? That does make sense. Can you reach that?
Yeah, but even selecting those with the best photosis, this is less than
It looks
one,
crazy.
1 per 1,000. It's too good for. We are hoping for 1,000 kilometers
Okay.
per second.
Yeah.
That's the number,
Yeah.
more or less.
Yeah. Yeah, so it might be that this is completely unobtainable, which is what I would have like started with as a base assumption. I thought it was worth, bringing up just in case I was wrong, or maybe people, think, there's something there, or I mentioned if there's enough galaxies that you give it to some poor PhD student to try, like 10 years from now, and they spend a lot of time looking at, being like, is that a signal or not,
Even you can think if I know more or less that things are here,
Yeah.
now I'm going to move randomly things, or I'm going to move just to have a higher signal. So perhaps you can even improve for this. I don't know.
Yeah, I mean, maybe if you
I don't-
if you said that the errors within this and you do tons of realizations and I don't know, maybe. I like I said, I didn't think that this was going to be the best thing, but I had to have something to discuss. And it was a question I had before I came, so. Okay, well, so those were my discussion points. I don't know if you had some things you wanted to add for us, if there's more, or if we're all discussed out. I mean, this has been a great meeting. We've had lots of discussion time, which also makes this a little hard because I think, we've talked about almost everything already. What's left?
Yeah.
The footprint.
No, that conversation.
I think that each one is very interesting because at the end it gives you the fuel masses. So with the emission lines that we have a star formation rate, so you can have hints of the star formation efficiency. This is an interesting point because, to my knowledge, there are only a few papers in the literature talking about the star formation efficiency. 2, 3, no more, with the stellar mass.
So then I have a maybe provocative question or devil's advocate question. I love neutral hydrogen, but if we're talking about star formation and star formation efficiency, do we need to be talking about molecular gas?
Yeah, well, if you want the full picture, you need both because one is the total fuel, and then is what you are really using at the end. That is molecular gas. So probably the conversion from neutral to molecular is related with the star formation rate. Perhaps you can go the other way around. You know the star formation rate. You know what is the molecular gas. I think that there are relations there. About
the tightest relation is between molecular and star formation rate. The atomic is not necessarily tracing the potential star forming gas.
That's the thing. So at the end, if you know the star formation rate, you know how many molecular gas you have. So you know what is the conversion between molecular and atomic gas. That probably means something in the galaxy evolution. I mean, in the sense that why a galaxy with similar H1 masses, someone makes more stars than others.
Yeah.
So do we understand that? Actually, you didn't mention this the other day. I don't know. So, the organization supposedly reorganize the universe and leave some pockets of neutral hydrogen. But I have no clue whether this neutral hydrogen is molecular or atomic, right? And then you're saying that you produce stars from atomic or from molecular.
So you need to go first to the atomic, then molecular.
First atomic and then molecular. Okay. And then this atomic is supposedly the one surviving the ionization. Somehow.
It's the one that?
Surviving the ionization, right? So how does this atomic
surviving the ionization?
reionization? Yeah.
Yeah, organized, but it should be, or that cools later. Yeah.
Okay.
It's a potential.
So we don't know much how how that gas appears, why it survived and so on. I don't know if there are people looking at this in H1 studies,
I mean, so in local universe, there's definitely people looking at how our galaxies are creating gas now, looking at low column density H1 because are they accreting gas? We kind of think they must be, but we don't really see evidence of it. For surviving ionization, I guess the picture I have in my head, don't realize on the moment I realize I'm not sure how accurate this picture is that the ionization is the intergalactic medium in between the galaxies, but within a galaxy, the gas that's in the disk of the galaxy
it's still there, right?
Yeah.
And actually, most of the neutral hydrogen is found in galaxies. We don't see much. Well, from the Lyman alpha, we know that the amount of neutral hydrogen in voids or in the intergalactic medium is tiny, it's small, right? Most, if I'm not mistaken, I think this is more or less correct. Most of the neutral hydrogen is in galaxies. Now, how it gets transformed, well, it was initially atomic and then it becomes molecular, and how it interplays with galaxy formation, I have no clue, right? And I don't know whether this is a hot topic for you guys or something you can explore from the star formation side.
Yeah, well, coming back to the ionization, it depends on the column density of the gas. So if it's low column density, then it's easily ionized. And if it's higher column density, then
Yeah, so the
it's like an
IGN,
onion type of things where you are in the outskirts, it's probably more easily ionized than in the center, where the column
Is there
density
I
is
mean,
higher.
I've heard, in the ionization context, I've seen many simulation outputs, and it's unclear to me where they have converged to a picture that everybody agrees upon. I don't know, in the sense that it was not, I don't know. I don't really know about this, right? So I don't know if you could contribute to this problem in some way.
Well, it's a complicated thing because it depends on many things like turbulence and
yes, it's a lot of physics.
Yeah, all of it.
yeah, so I mean, I think I'll say people like how gas goes from atomic to molecular to star forming is a very active area of research that people want to understand. Simulations, cosmological ones, put it in different recipes. I think there are small scale ones that work on it in detail. I also see, I'm really glad I joined the Zoom because I can see someone has their hand raised. So Miguel, if you want to contribute.
Yeah, thanks. I have a question regarding the star formation rate that you guys in JPass or J plus determine. So is there any bias? Because my understanding is that you basically do this by using H alpha, and H alpha suffers from, when you look through a large column density, you basically are completely biased, in my opinion. So how do you take into account all these things? Apparently you seem like easy. We get the star formation rate, and then it's a matter of H1 or H2, but I'm not completely sure. But of course, I'm ignorant on this. So could someone comment on this?
I think Rosa wants to reply to that.
Well, there is several ways where we can get the star formation rate. One, it is related with the H alpha, that in fact it is the star formation rate, recent star formation rate, but other we can get from the fitting of the G spectra and getting the star formation history of the galaxy. In that way, we can get a star formation rate over several phases of the evolution of the galaxy. So that means that, for example, we can get it the star formation rate in the last, for example, 1 giga-year or 100 million year. That probably is more in agreement with the star formation rate that you derive from the continuum, radio continuum.
But also it depends on the kind of stellar population that you want.
That's why we trace the star formation history of the galaxy using evolutionary synthesis model to constrain the stellar population on the galaxy.
In galaxies with relatively moderate star formation rates, the extinction is not that heavy. If you go to hundreds of solar masses per year, things like that, then there might be a deeply obscure population in the galaxy. But if you are at 10, normal galaxy, H alpha is not going to be severely biased.
In any case,
if I may add something, that's exactly the case. I mean, I agree with Juan Antonio. You are right. But maybe one of the important questions about star formation history is that one goes back, with higher redshift, the contribution from luminous infrared galaxies and ultraluminous infrared galaxies gets much and much higher, right? And these, we know that when you look towards the central regions where most of this star formation activity is taking place, they are heavily obscure, right? So no way, my understanding is that when you look at these kind of galaxies, and this is important, when you go back in redshift to higher redshift, this is a serious issue. So, this is a problem, but on the other hand, this is an opportunity. So I just throw my contribution to this discussion would be, one could try to think in terms of also, key science projects for SKA, or questions that are difficult to answer but are very important, and this is precisely to measure confidently star formation rate across the universe. And probably that doesn't come from just using either only radio or infrared or UV or even, you know, your optical observations. Probably it's a combination, but that could be a very important question to answer. And I think these these synergies, not even beyond JPass or and SKA, that could be something really important. I'm not completely convinced of using just the star formation rate that we derive or you derive, or even we don't understand correctly. The radio continuum is not actually the real tracer. It's far infrared to radio correlation, and this is not completely clear that it applies, through the whole history. So maybe that could be something to think about, a possible good project. I don't know. Just thanks a lot.
I agree that in fact the galaxy is very skewed, so that means that most of the star formation rate will be sampling or tracking by the far infrared or radio emission. But what we know too is that most of the galaxies, they are building the Madao diagram, and they are contributing to mostly to the stellar mass, the cosmic star formation rate, are normal galaxies. Our galaxies, they are in the main sequence. For this galaxy, the extinction is not really very important news. Or at least we can know how to correct it at the optical wavelength.
Yeah, I was going to stress what Rosa is saying now at the end, that there might be dust extinction that might bias the H alpha flux as a tracer of star formation, but we have ways with only JPass data or J+ to estimate how much if you fit the SCTs, you get a reasonable idea of how much extinction is happening. And also probably with JPass, we can actually measure the H alpha to H beta ratio, the decrement, and estimate from that. Of course, this works if the extinction is not so extreme that you don't have H alpha.
Yeah, you need something to correct.
But yeah. But I also agree with that. Going multi-wavelength and chasing different tracers will add a lot more, not only measuring the star formation rate, but understanding what is happening.
Yeah, indeed. Also, for example, in D+, what we made the analysis in the local universe, we take a look to the impact of inclination, in the sense that you expect that edge-on galaxy has less star formation than a phasor. And of course, for the disky ones, we saw that effect. So you can measure it. So there is an impact of the extinction for sure, and you need to take care and override your limitations. That's all. We are all have our limitations in the studies.
Yes. No, and I think we're here talking about the sorts of synergies. I think we can all agree a multi-wavelength view brings a lot of value. And I think I really appreciate the point you made, Miguel, that understanding like radio as a star formation tracer, I think is not a given. That it correlates with infrared. We have some ideas of what causes the radio emission, but that this is, I'd say, an active area of research. And yeah, in order to do that with the SKA, we're not just going to be able to blindly trace the star formation. We're going to have to actually understand how the radio works as a star formation tracer.
Because right now, what I saw in the literature is people doing stacking, basically, because you cannot reach, you're stacking in the continuum, in Cosmos or in deep surveys. You select your galaxies and then you make the stacking and give you some average properties, and you relate with the star formation, and that's your star formation history. Probably now, with the SKA, we can go really to individual sources and do demographics, which is something that right now is not possible. But we have surprises in the sense that, Rosa said, we found a lot of obscure objects that were missing before, or not, or we were already okay, and we are seeing the right, most of the objects that make the star formation history. Who knows? We will see.
Any other last points for discussion?
I've got one, but I guess I'm afraid that most people are really uninterested in this. Has to do with I would like to ask you guys from the H1 community, when do you expect the first maps of intensity, high intensity maps would become available? I know that LOFAR data is private, right? Or I think this is correct.
Okay.
What is the forecast?
Yeah, so I mean, so the intensity mapping happens at different redshifts also, so I don't know what redshifts you're interested in.
It's low
So like the
redshift.
low far stuff is epic of ionization, that data processing is painful. I think MWA Gleam, other experiments are doing the same thing. Then there are also experiments that are looking at like kind of intermediate redshift. Don't ask me what the range is, I don't fully, maybe around 1-ish. There's projects with Meerkat that Mario Santos is leading. I know they've had a paper out already of some first results, and there's MeerClass. There's things that Chime is doing. I honestly don't know, like about that data, like status of it when it will be public or things. But I mean, I'd say it's very active experiments happening right now. So I expect we'll see things. Like I said, I know there are some first Meerkat-based results, and there have been first Chime results also.
I know for Meerkat, I know they're around redshift 1 or even below redshift 1.5 or so. But that's Meerkat, that's SAPS, if I recall correctly.
Yeah, and so then Chime, I know, so I saw a great talk from Richard Shaw last EAS in Valencia, and I know that because I was on the SOC for the session, so I should remember more of it than I do, where he showed some of the Chime results and looking at things, and it was actually, and as I remember the talk, and I remember really enjoying, I remember I was at the talk, and I remember I really enjoyed it. Do I remember like the messages? Not as much, right? But they had some great stuff. But again, like in terms of what you're looking for, I don't 100% know, or if they just have results that are published as opposed to like data that's available. But I think, if you're thinking about Northern Hemisphere things, Chime is probably for intensity mapping the people to talk to, so. Wait, I was gonna say, so we'll come back to that, but I also see that Lourdes has raised her hand, and so I am trying to make sure that the online people are acknowledged. So Lourdes, you have something to add to that?
Not to that, I have another kind of comment related with.
Here, were you going to stay on that topic, or are you moving?
No, just saying that Lourdes.
Sorry.
Okay.
I was going back for a second to what we were saying before about aperitif. I found it in the letter. And just to confirm, the only JPass seed that is covered by, at least by the current, it's mini JPass. So the star that you.
Yeah. Okay, great. All right, so Lourdes, please take us to a new discussion topic or shift us back to a previous one, whatever you are planning.
Yes, no, it's just related with what Alejandro just said about this overlap with aperitif and JPass that was discussed before. And I just wanted to mention that because we have already running advanced processing of aperitif data in collaboration with Kelly when Kelly was at the Institute, and we continued collaboration and producing catalogs and advanced data products. I think that it would be very interesting, of course, if all this work in the sense of property of the data and all these kind of other things, but from a practical point of view of collaboration, I think it would be very, very interesting if we could, I think we need to study this, but we could provide, I think, from the Spanish Regional Center, support to this combination of JPass and aperitif data, if this is happening at some point, because we already have been running this at the ProtoSRC. So maybe providing a platform for this collaboration would be quite natural, given the combination of the JPass expertise at the Institute and the collaboration with aperitif. So this is something I think we need to study the details. I think it needs to be defined by aperitif people, but yeah, I just wanted to offer this and put this on the table, at least for study.
Well, thank you for that. I think that's a great offer, and as you said, a natural one, because basically all of the nice H1 data processing has been done on the Spanish SRC already by Kelly. Yeah, and I think I'm definitely open. I think we could definitely define common projects or things. I don't think we're gonna do that now in the discussion session. I think it's something to follow up later. And I guess, we should do that, and to know that we have the Spanish Proto-SRC as a platform for doing that, because it might be, there's lots of data products Kelly's already produced, but maybe we say we need to focus on a specific area or take the processing a step further or something. To know we have a platform for that is absolutely excellent. So thank you. Okay. So with that, I think we will wrap up. I don't know where we are on the agenda, but I think it's also, whatever. We're, you know, I know where my stomach is, which my stomach says it's 15 minutes past lunchtime because I have adapted to Dutch times.
Breakfast.
Yes, and I hear that that's second coffee here now or something.
Almuerzo, es almuerzo time.
Okay, well then I will go ahead and leave the Zoom, and I think Marie Lou is going to.
This is like
Or
the
maybe
shy,
we can
this is second breakfast.
Can share by Zoom.
Whatever you prefer. You should probably have 1 second delay or something like that between.
Okay. Bueno,
But no es, no es crítico.
Function. Okay. How does this work? Is it pointer?
Yep. You want the air mouse or you want the pointer? Let's try the air mouse.
There's a pointer.
Okay.
Okay. Okay. All right. Hello, everyone. It's my turn. Okay, so I was giving the task by my scientific organizing committee to do this concluding remark. What an honor and a little bit of pressure, right? And so I'm going to do my best to summarize these 3 very intense days that we had. Quite intense, I would say. I cannot summarize all the science that people have been presenting. I think I would not do a good job of doing that. You know better than me about your science, but it was really nice to learn about those. And I think that all the talks are going to be recorded and available so that we can go back. And so hopefully this meeting will create these tools that we can use to better understand each other, right? This is the goal. So I'll prepare a couple of slides to talk about sort of a summary of this meeting. I know a lot more about JPass, J+, all these surveys, this beautiful telescope, these cameras that have a very large field of view. As far as I understand, I think the JPCam has a 1.4 by 1.4 degree, right, in the sky, which is it has been compared with the full moon, all of these things. But what I like to compare it is with the projection in the sky of the SKA white book. Okay? So if you place it, I calculated this. If you place it at 12 meters, that's how big this field is. So quite impressive, right? Okay, we have been giving this amazing tour of the observatory. Thank you about that. It was amazing, and also of the portal, how to get access to the data. Okay, we discussed a lot about the observation strategies, about these seeds, these fields around which we grow. This seems to be very interesting and complex and emotional somehow to some people here. We've talked also about open time, some open time that might be offered in the next year or something like that. Future call for proposal with the JPCam. There might be opportunities there. We can continue to discuss this. On the SKA side, the telescope is under construction. It seems to be very fun to be constructing those telescopes. We have a timeline here. It seems far, but actually some data are coming quite fast, right? It's not an optical telescope. You don't need to build the whole thing, the instrument and everything before getting the first data. So it's kind of a process where you have these antennas that are being built. And so maybe in 2026, 27, we're gonna start to have those first data. So it's coming, it's quite exciting. What else? Oh yeah, the jargon of SKA, right? These key science project, these science working group, which are not the same, right? We have
talk about those concepts with Wendy. So they are not the same. They might be related, but I think one of the important points is to join the science working group. They are open to multi-wavelength expertise. Okay, you don't need to be a radio expert. I want to emphasize this. To join this is the best way to keep in touch with the SKA. And yes, okay, this talk is very biased by my because and this is the distribution of time. So we learned that the key science project are going to take a large amount of time, the portion of time on the SKA, right? But so far, no time have been given, and we're discussing how it's going to go in these science working group. Okay, this is the slide I should have probably started the meeting with, which is how how the SKA mid and SKA low are gonna overlap with the JPass and J+ footprint. As it has been said before, we had a lot of discussion, some calculation as well on how these tools are overlapping. We discussed potential strategies to overlap these things better. But then things get very complicated because of the moon, apparently, and then how we grow these seeds and everything. And this, honestly, I don't want to go there. Okay, but I think the important, well, actually, also we already have a logo, apparently, so that's really nice. But one thing that we should probably, and it has been mentioned in discussion yesterday, where I think perhaps we were quite tired, but it's important to get centered on science case. I think this morning we had really made a lot of progress, I think, in that direction, perhaps starting just by cross-matching our catalogs. This is some screenshot of some slides that I've taken from your talks. I think we're going in this, if we go in this direction, it's probably better, and then after that we can adjust how we do this, right, in terms of strategies. Okay, well, okay, but that's not just this. We have other radio telescope, not just SKA. We have this nice summary slide that Javier made. I don't know if he's gonna be happy if I'm showing this. And so we've talked about other radio telescope, right, that are already available, that already have a lot of data product, okay? It might be hard to understand each other, right? But we already have tools to deal with that. So hopefully this meeting, as I said, we have created tools, right, to try to communicate better between each other. So, and as I said, there's a lot of data that are already available that you can prepare before the SKA. And actually, this is something I like to show. So this is all this global family of precursor and pathfinder telescopes. In green are those that, as far as I know, are have open time that you can apply for. Okay, others have. I mean, some of them also have surveys with data product that are already available. We have some of us have presented this, so it's good to have a look at this. Okay, even though they are in Jansky or whatever. Okay? And as I said, again, join a science working group, and yeah, let's start to work on with those data already. A common challenge right, is the large amount of data that we have. We are sharing this tsunami, has been said like that, of data. Thankfully, we have Tamara and Javier to help us deal with this. And it's been interesting to see that we are looking toward green solutions for that. That reproducibility and data access is really something that we really agree on. So that's really nice. One word on the SPSRC, which is fully operational, that provides computing resources, support. What Lourdes said just before, emphasize this. So this is not so much to access the data from the Pathfinder precursor, but more to give resources on how to deal with those data. Another challenge, perhaps, is those funny satellites that we have to deal with that influence also both radio and optical. but we have some, institute. This is the institute that we were taught. I think Wendy, you mentioned it. That hopefully we will deal with this a little bit better. So a challenge, not a problem, right? And that's it. I'm gonna just conclude here. Thank you, everyone. Thank you for the scientific organizing committee who built this amazing program. The local organizing committee, of course, without whom, Juan, thank you so much for all the help, Luisa, and everyone here, people that chaired the discussion session, the invited speaker that came here, everyone who contributed to this meeting, and SKA that also was here. And the beautiful visit that we had yesterday was very interesting. We were like kids in the observatory. It was beautiful. And that's it. Thank you very much.
If I may, I wanted to also say that I think that Marilu didn't know when she accepted I suggested her to be the chair of this meeting. She didn't know what she was saying yes to. And I think it was a great summary, and I think she deserves also recognition. So I'll clap here. I ask you for her.
Next meeting at the on an SKA site in Australia or South Africa.
Okay. Okay, maybe. I'll think about it.
Germany 2025, SKA Science.
It's true, it's true.
What in Germany?
I don't remember. Do you remember me? Sorry, what's the question? The SKA Science meeting in 2025.
It's in Berlin, Germany in 2025.
Germany. Mm-hmm.
And I think the date is probably May, early June, I think. The Prime Minister.
We will send you out.
All right, thanks.
Thank you very much.
Goodbye to the online people.